Good morning, everyone. My name is Myung-suk, and I'll be presenting the work Asgard protecting on-device DNNs with virtualization-based TEs. This is a joint work with my colleagues Mini, Jungyo, and my advisor Do-kyung-sung from Yonsei University. Like cloud-based AI services, on-device AI does not require sending user data to the server. However, on-device AI requires sending these on-device CNN models to user devices, and these models are often a highly valuable intellectual property that are trained with a lot of resources. So our goal here is to protect on-device models from malicious device owners. A lot of prior work tried to protect on-device models with Arm TrustZone. As some of you might already know, the blue area is the secure world, and then the gray area is the normal world. The security critical services like key management runs at a EL0 secure world as a trusted applications, and then the EL3 secure monitor enforces isolation between the two worlds. A line of work decided to assign the accelerator to the secure world and support hardware accelerated inference. And then the second line of work decided to leave the accelerator in the normal world. And we will briefly talk about the first line of work. During device boot time, the secure world memory is statically partitioned from the normal world memory. The secure world often has a small memory size. Also, the secure world often runs a vendor-specialized trusted OSs, so it is difficult to reuse the existing accelerator drivers from the host Linux. Because of these limitations, the works in 2022 decided to employ a fully written minimal accelerator drivers in the trusted OSs, but this is missing a driver compatibility. So the other work decided to add an additional component to the EL3 secure monitor, but this requires modifying the most previous component in the system. So the second line of work decided to leave the accelerator in the normal world. This work decided to offload less sensitive operators in the normal world because sometimes we cannot fit the entire memory in the secure world. But this does not provide a full protection for the entire DNN model. So the work in 2023 decided to only offload linear operators in the normal world and have the model weights obfuscated. But because model weights are obfuscated, this requires de-obfuscating and obfuscating all intermediate tensors that are passed between the two worlds. And these are adding an additional runtime overhead. So we create a first system that protects on-device DNNs with virtualization-based TEs. The TEE here is a virtual machine running at EL0 and EL1, and we have the EL2 hypervisor to enforce isolation between the TEE and then the REE. Our design here is to directly assign the accelerator in the VMs and also support dynamically reassigning the accelerator among multiple virtual machines. The upside of our design is that it has a good driver compatibility because we could use a commodity OSs like Linux in the VMs. And second, we do not have to modify the EL3 secure monitor, which is the most privileged component in the system. And finally, we could provide a full protection for the entire DNN model because we could dynamically set the memory size for the VMs. However, there are still some challenges with our design. They are runtime overheads and a TCP overheads. This is because even though we directly assign the accelerator to the VMs, delivering the accelerator's interrupt to the VM will still incur an additional runtime overhead. Also, if we had to reassign the accelerator to another VM, this will incur a moderate amount of overhead. For the TCP, we have to use a full commodity OSs in VMs, so the TCP will be bigger than using a vendor-specialized trusted OSs. Finally, we have to add an additional component to the EL2 hypervisor to securely support accelerators in the VMs. And we address all of these challenges with our own system and application level optimizations. As you might already know, the accelerator could do a direct memory access to the VM's memory. But we want the accelerator to only access the VM's memory and not the other parts of the system. So we have the IOMMU in the middle that enforces memory access policy for the accelerator. The IOMMU will work with its own page tables, and we have the EL2 hypervisor to control the IOMMU. Doing this will involve adding a full IOMMU driver into the EL2 hypervisor, which will bloat the platform's TCB. So we split the IOMMU driver into the trusted part, the trusted and untrusted parts. So the EL2 hypervisor will delegate a resource management part of the IOMMU driver, but it will still keep the resource isolation part of the IOMMU driver, the IOMMU driver. Let's say we had to reassign the accelerator to T number 2. A straightforward approach would be deleting the existing page table entries for T number 1 and creating a new page table entries for T number 2. But doing this for a few hundred megabyte size VMs would incur a moderate amount of overhead. So what we do here is to have the hypervisor to maintain all page table entries that were created during the VM initialization, and during the reassignment, we have the hypervisor to reuse this existing page table entries so we could minimize the runtime overheads coming from reassigning the accelerator. We also have to securely reassign the accelerator. The accelerator could have a leftover data, like in their device registers, and we want these leftover data to be wiped out when they're reassigned to another VM. So we first remove access from T number 1 for the accelerator, and then we have the hypervisor to fully reset the accelerator so that all the leftover data is wiped out from the accelerator. Finally, we grant access to T number 2 for the accelerator. Moving on to the next challenge, delivering the interrupt to the VM will incur an additional runtime overhead. The accelerator will first deliver the physical interrupt to the host kernel, which is out of the TCP, and that will do the interrupt management of the system. The host kernel will then inject what we call virtual interrupt to the VM, and this will involve a multiple VM exits and entries because the host kernel has to receive acknowledgement from the VM that the VM has successfully received the interrupt. And the host kernel also has to unmask the physical interrupt so that the accelerator could resume sending the physical interrupts back again. So during DNN inference, these interrupts will incur an additional runtime overhead. In a DNN model, there are NPU-supported operators and a CPU fallback operators. As you can tell by its name, CPU operators are operators that are not supported by the NPU. After executing the NPU-supported operators, the NPU will deliver the interrupt to the VM so that the VM could then execute the next CPU operator. In our default execution order, the CPU operators number 3, 6, and 9 will be separately executed. So in total, 3 interrupts will be sent to the VM. However, in our exit coalescing execution order, we coalesce all CPU fallback operators that are not data dependent to each other. So in this example, we could coalesce operators number 3, 6, and 9, so that in total, only 1 interrupt is sent to the VM. And we discuss how we address other challenges in the paper. For implementing our prototype, we use ARM 8.2 legacy SoC with an integrated NPU. For running a protected VMs, we use Android 13's protected KVM, and for a virtual machine monitor, we use Google's CrossVM. And our design will work with a legacy SoC. We first measure a DNN inference latency with a MobileNet V1 model. For the prior work, it involves offloading linear operators in the normal world, and it also has to de-obfuscate and obfuscate all intermediate tensors. So these are adding an additional runtime overhead. On the other hand, even in our approach, even though we reassign the NPU before running a protected inference in the VM, our approach is around 4 times faster than the prior work with a MobileNet V1 model. We then evaluated our exit-coalescing execution order. For the SSD models, it has a highly parallel DNN architecture because it has a multiple parallel feature extractors. In our prototype, we have reshape and transpose operators as a CPU fallback operator. For the light transfer models, it also has a parallel DNN architecture, and we have reshape operators as a CPU fallback operator. For the SSD models, before applying our exit-coalescing execution order, the runtime overheads were around 2 to 3% compared to running inference in the REE. And also for the light transfer models, the runtime overheads were around 15 to 33% compared to running inference in the REE. After applying our exit-coalescing execution order, we were able to remove around half of the exits from these models. The runtime overheads are now 0 to -1% for the SSD models and 3 to 6% for the light transfer models. And more evaluation results like TCB size, inter-delivery latency, MP reassignment latency, and memory usage is available in the paper. In conclusion, we designed the first system that protects on-device DNNs that is based on virtualization-based TEEs in legacy SoCs. And we showed that the virtualization overheads could be contained with our own system and application level optimizations. And we encourage you to check our paper for many more details. Thank you for listening.
Okay, thank you so much. So we have time for perhaps one question. Okay, so maybe I'll ask a kind of high-level question. So this model is kind of encouraging clients to use devices that have the TEE capability, right?
Right.
So I wonder if this could kind of cost, like Google, for example, Gemini customer base, because now if you're forcing, I only will ship my Gemini to you if you have TEE on your phone, and what if my phone doesn't support it? And what if, like, for different phones, the TEE implementation you should probably adjust for different phones, right? Yeah. So I was wondering from a business kind of point of view whether that's kind of presents itself as an obstacle kind of for this approach.
You mentioned that you have to do the adjustment for every devices, right?
For different types of like TEEs, right? Because they use different implementations, and also some of them, I assume, some phones still don't have the capability, right?
Right. Our target is a legacy SoC, but we use Android's protected KVM for our implementation, and a lot of Android devices already have protected KVMs. So we believe that our design will already work with the existing Android devices, but we will still have to make some slight adjustments for every devices. For example, for resets, resetting the NPU will look different for every other devices.
Okay, sounds good. So we're out of time. The next session will start, but I encourage everyone to please engage with the authors offline. Thank you so much.